I'll start. So today we're going to see a particular limit of AdS CFT, which is the so-called plane wave limit. So we are going to see that certain spacetimes called plane waves arise as limits of AdS. So first we're going to discuss some features of plane waves. So we're going to say what a plane wave is. And then we're going to discuss the propagation of a particle in a plane wave. So we're going to solve for particle geodesics moving in a plane wave. And then we're going to solve the quantum mechanics of a string moving on a plane wave. And then we're going to see how these plane wave spacetimes arise as limits of anti-de Sitter space. So we're going to do a particular limit of AdS cross S, and then we're going to get these plane waves. And then we're going to understand what this limit translates into in the gauge theory. So this limit will translate into a particular limit of the gauge theory, and so we're going to try to understand that. Okay. So this will be a particularly nice limit, because in this limit, one is going to be able to actually reproduce the string spectrum. So we're going to find some string spectrum on the plane wave, and that we are going to be able to reproduce that spectrum from the gauge theory. Okay, so what is a plane wave? So a plane wave is a spacetime so it's a spacetime that has the following metric. So it looks like flat space. So if we had this metric, we would have the flat space metric, but it differs from the flat space metric by typically some quadratic functions of x plus times, let's say, yi, yj. Okay, so it has this additional term in the metric that is quadratic in these transverse variables y, and it could depend on the coordinate x plus. We are going to be mostly interested in cases where there is no x plus dependence here, where this matrix is just constant. And furthermore, we are going to restrict to the case where this matrix is just diagonal, so we have something like y squared. Okay. This matrix in general can have positive and negative eigenvalues and so on, but for the moment, let's say we have just some constant times y squared. Okay, so now we can, we'd like to understand how these spacetimes look like. I mean, what the particle in this spacetime looks like, what would do. And in order to do that, it's convenient. So we write the particle action. G mu nu. So G mu nu will be the metric that is appearing here, plus ME. So this is the action for a particle. And now we, okay, so now we insert the metric that we have here above. Well, this action is reparametrization invariant, so we can choose any reparametrization we like. And a particularly nice gauge fixing for the reparametrizations is to choose this so-called Lycon gauge, where x plus is equal to tau. And then if we do that, then this action simplifies. So we have d tau, and then so we, I guess here is factor 2. So here when we insert this metric here, we'll get e to the minus 1 times minus 2 x dot minus. Okay, that's from this term. Plus minus mu square y squared. So that we get from this term plus y dot squared. Okay? So we get all that plus ME. Okay, so now E appears just linearly, appears algebraically in this equation, so we just solve the equation of motion for E, and, well, actually, we do something slightly different, sorry. Here we see that x minus dot appears linearly, and so we compute, so this action is invariant under translations of x minus, so there is a conserved momentum, which is p minus, which is the derivative of the Lagrangian with respect to x minus, and that is equal to, so that should be equal to minus e to the minus 1. I'm getting the sign wrong. Okay, well, I don't know why I'm getting the sign wrong, but this is should be equal to minus e to the minus 1. Okay, so so p minus will be negative, and we can and it's constant, so this will be a constant. So we can replace then this back into the action, and we obtain an action for the y variables. So now tau became x plus, and so we have minus p minus y dot square minus mu square y square. Okay. So we see that the action for y is the action of a harmonic oscillator. Okay. And well, p minus is just some constant. Okay, so so what is this saying? So this is saying that if we fix a particle with p minus, then in the y direction, so if we draw the motion of y, so if we start the particle at y equal to 0, it will stay at y equal to 0 as a function of x plus. So let's say this is x plus. So as a function of x plus, the particle sits at y equal to 0. So that okay, so that so a particle that, let's say, has x minus. So suppose you have a particle that has x minus equal to constant, y equal to 0, and x plus that changes. So that's a lilac geodesic. Okay. Now you can consider a particle that if it starts with some value of y, it will start oscillating around x plus equal to 0. Okay. So this we can interpret as saying that, well, there is a gravitational force that is pushing the particle towards y equal to 0. So the this metric is sort of focusing in this direction. If you start with two geodesics slightly separated, these geodesics will want to approach each other. Now, if we had in the metric, if mu square had the opposite sign, let's say if we had plus mu square, then we have the opposite sign here in the Lagrangian, and what we would get is that the geodesics would be going away from each other. So this is some other possible behavior. It depends on what kind of plane wave metric you get. You'll get these different behaviors. Okay, so we get all this. Now we can compute the energy of this geodesic, and so the energy will be so the Lycon. So the Hamiltonian for this system will basically be minus dx plus, well, with some I. And so essentially, so the energy will be for this system will be the momentum minus p plus, where p plus is the momentum conjugate to translations in x plus. So so now, okay, notice that, so it's convenient here to work with the conserved momenta, the momenta that have the index down, okay? So the momentum is always the momentum, so this metric has translation symmetries in x plus and x minus, and the conserved momenta are these ones that have the index down, are just the derivatives with respect to the positions. People who work in Lycon in field theory sometimes put the index up, in flat space, we can just put the index up, it's just multiplying by some factor, p plus, p minus. But in this case, p plus, p minus are not conserved. The ones that are conserved are the ones that have the index down. They have the minor problem that they are negative. That's why people normally choose them with the index plus, so that they're positive. Okay, so now that's the classical mechanics of a particle in a plane wave. We can do the quantum mechanics of a particle in a plane wave. And so for the quantum mechanics, basically all we need to do is just quantize this action. And so we'll, when we do that, so we'll obtain a Schrödinger equation. So if we have a scalar field phi, which is a function of x plus, x minus, and y, so we choose it with definite momentum in the x minus direction. That's equivalent to what we said there of fixing the momentum in the x minus direction. And now we have some function of only x plus and y. And this function obeys the Schrödinger equation for a harmonic oscillator. So d plus of phi equal to mu, let's say dagger A. So this is the creation operator for the harmonic oscillator. So it's just the standard Hamiltonian for the harmonic oscillator. Okay. I realized I've forgotten this term here in the energy. Let's see. Well, first of all, I've written here, I forgot an m square. So there should be an m square over there. And so this is m square over p minus. Okay. Up to some signs. Okay, so this is the Schrödinger equation that we get. And, well, so from here we can find the spectrum. So we can furthermore say that this is, so we can say minus p plus is equal to this quantity. Okay, minus p plus is mu n plus a half plus m squared over 2 minus p minus. So p plus and p minus are both negative, and we have this sort of spectrum that looks roughly like a harmonic oscillator spectrum. I mean, this harmonic oscillator spectrum is coming from this force that pushes the particles towards the center in this transfer space. Okay? So the particles look as if they were in a gravitational potential well. In that sense, this remember that in AdS we have a similar property that particles are pushed to the center of AdS. Okay? So here is somewhat similar. And that, of course, will not be a coincidence. Okay, so far we've discussed particles on plane waves. So now we'll discuss strings on plane waves. So what we do is we come back here. So we come back to this metric, and instead of considering this particle action, we consider the action for a string, which has a similar. So we use this Polyakov form. It has a similar form, and what we will get is that after we go to Lycon gauge, so you probably saw the derivation of, well, you started with the Polyakov string, and then you can go to Lycon gauge. And in Lycon gauge, if we didn't have this term in the metric, so Lycon gauge is again for a string is x of sigma and tau is equal to tau. Okay. So this is the Lycon gauge choice, and then again there is a conserved quantity p minus, and so we fix p minus. So again fix p minus, and in the end the action in Lycon gauge will have the form 1 over 2 pi alpha prime integral dt integral between 0 and so the length of the string is proportional to p minus. And so we have the sigma, and so we have 1/2 y dot square. So we only the transverse coordinates appear here, and so we have this action. Okay. So this is the action in light cone gauge in flat space, and the only difference now is that we are adding this term to the metric, okay? But in the sigma model action, once we make this gauge choice, this will just be a constant, okay? So all that will happen is that here in the light cone gauge action, we are similar to what we had in the particle case. We had this mu squared y squared, okay? So this will be the action for a string propagating on this metric, on this metric here. Now, this would be a bosonic string propagating on this metric, but we might be also interested in the superstring. So in the superstring, we will have some fermions here. So I, S, ds. So this is a particle which, so we have these fermions on the worldsheet that are also space-time fermions. They transform in the spinor representation of SO8. So they transform under the orthogonal group, okay? And under the group that is transfers to the light cone directions. Okay, so these are in the spinor of SO8. Okay. So the string is moving in 10 dimensions, and these are the 2 directions transfers to the light cone. Okay, so that's the action for a superstring propagating on this metric. But in addition, we could have some, besides having this metric, we can now add some Ramon-Ramon fields. And it turns out that you can add Ramon-Ramon field with component. Well, let me first explain one thing. This metric is not a solution to the type 2B supergravity equations. Okay? It's not a solution because R++, so this component of the Ricci tensor is non-zero and is of the order of mu squared. Okay, that comes from this term. Okay, so this is not a solution. However, you can make it into a solution by adding a constant Ramon-Ramon phi-form field strength. Well, there are many ways in which you can make this into a solution, but one particular way is to say, well, this is non-zero, but will be equal to f plus mu1 mu n, f plus mu1 mu n, okay? mu5, let's say, mu4. So we have phi-form field strength and is some constant. And if we take this to be some constant equal to mu, then this equation will be obeyed. Okay? And one can also check that all the other equations are also obeyed. So in other words, we end up with a spacetime that has this metric, this plane wave metric, and a constant Ramon-Ramon phi-form field strength with only plus components. So in other words, let me write it down here. So we have f plus 1, 2, 3, 4 equal to f plus 5, 6, 7, 8 equal to mu. Okay. So this is a self-dual phi-form field strength that is constant. Okay, if you add this phi-form field strength, the Ramon-Ramon field strength interact on the worldsheet with the spinors on the worldsheet, and here they will interact in such a way that they add a mass term mu to these spinors. Okay. So you'll get some mass term that is mu times some matrix in SO8 times S. And well, this matrix I is related to the indices that this thing has. So I turns out to be something like gamma 1, 2, 3, 4. Okay. Anyway, so that this is not very important. What's important is that you get the mass term for the fermions. So this term looks like a mass term for the bosons. So the bosons are all harmonic oscillators, including the zero mode, including the mode that is constant in the sigma direction, still a harmonic oscillator, and similarly for the fermions. Okay, so after all this, we can simply write the, so as analogy with what we wrote here for the particle, so So here we had this Hamiltonian for the particle, and we can write a very similar Hamiltonian for the string. And maybe I could write it just below. For a string, so this was particle. And now for a string, we just have a similar expression where minus p plus, which is the Lycon Hamiltonian, so it's the Hamiltonian for this action, is basically a sum of harmonic oscillators of this type. So for each mode, we'll have a harmonic oscillator. Well, maybe I should. So we have a sum over n from minus infinity to infinity. Let me call this big N just to make it the notation. So we have some occupation number for each harmonic oscillator mode, and each harmonic oscillator mode has frequency n squared over alpha prime p minus divided by 2. Okay. Now this n is the following thing. So if you take the y of tau and sigma and you expand it in Fourier modes in sigma, so you get a yn of tau times e to the I n sigma over the distance. So the distance is, well, that, so in 2 pi over pi alpha prime p minus, okay? So anyway, so you get here 2 pi over L. L is the length of the world sheet. And so notice here that n positive are like, will be like the left movers, and n negative will be the right movers. Here we have the sum over positive and negative n's. And even for n equal to 0, we still have a non-zero frequency. Of course, this total frequency for the harmonic oscillator is the sum of the term of the mass term we had plus the p squared. This is just the usual relativistic expression for the energy for a massive particle in 2 dimensions. Okay? Are there any questions? Yeah. Capital N is the total occupation number of the mode with this frequency. This sums the occupation number of all the bosonic and fermionic oscillators with this frequency. Okay? Of course, for bosons, you can have n that is very large. For fermions, n can just be 0 or 1. Yes?
Didn't satisfy our gravity equations without that term that was
well, if we are in Lycon gauge, it's hard to understand the supergravity equations. But if we ask, well, suppose we don't have this term, and we ask, well, we have this Lycon gauge action. We write the covariant form of the action, and then we demand that that action is conformal invariant, then we will find that it's not conformal invariant. Okay? So if in that covariant formalism you add this term, then you find that the action is conformal invariant. So conformal invariant in the covariant formalism is what ensures that the gravity equations are obeyed. Of course, if you don't want to do that, you can just write down the supergravity equations before you do any Lycon gauge choice, make sure they are obeyed, and then okay. Okay, so now, okay, so this is the spectrum of the theory. However, this spectrum needs to be supplemented with one constraint. So this is basically what we've written so far is a spectrum of a massive theory in 2 dimensions. So we have the world sheet is a circle, and we have all these massive particles, which are bosons and fermions, that can propagate on the world sheet. Okay? And the spectrum is the spectrum of this theory. And this needs to be supplemented with one constraint, which is that the momentum in the sigma direction is equal to 0. And this is just equal to the sum over n of n times n. So this should be 0. Now this comes from the fact that we should have, well, in the original string world sheet, we had reparametrization invariance in both tau and sigma. And when we fix Lycon gauge, there is still a residual reparametrization invariance. under constant shifts of sigma. Okay, that's some residual gauge symmetry that wasn't fixed. So translations in sigma is a gauge symmetry, and so the corresponding charge should be set to 0. That's one extra thing. And if we impose this constraint and we have this, so that's the full spectrum. Now, in the limit that, so here the physics will depend on whether mu alpha prime p minus. So we will now, the physics will be different depending on whether this is much smaller than 1 or much bigger than 1. So if this is much smaller than 1, then basically what we have is that mu is very small here. We can neglect mu. And the formula we obtain after neglecting mu is just the formula for the string spectrum in flat space. So in this limit, we get the flat space spectrum. Right? So this limit corresponds to basically choosing mu to be very small. On the other hand, if mu alpha prime p minus is much bigger than 1, then we have something very different from flat space. So this is some highly curved space. Okay. So in pictures, what this would correspond, so this situation, we had this plane wave that is filling this harmonic oscillator potential from this term in the metric, and the size of a string, which is given by alpha prime, is much smaller than, let's say, the typical width of this potential. Okay. So this particle feels more or less as if it is in flat space. It's a weakly curved flat with some weak curvature. On the other hand, in this case, we have this very confining harmonic oscillator potential, and the length of the string is much bigger than the size of this confining potential. So this is a very highly curved situation, and the spectrum is very different from the spectrum in flat space. Now, notice that whether we see the space as close to flat space or highly curved depends on p minus. Okay? So it depends on how fast we are moving through this space. So this is a space that is not boost invariant in the x plus and x minus directions. So it's translation invariant but not boost invariant. And as we do boosts, we can change the coefficient here. So okay. So the invariant quantity is this mu times p minus. So going to large p minus is equivalent to going to large mu and keeping p minus fixed. Yes. Yeah, yeah, it's arbitrary, and we said that we could change it by doing boosts. Well, 0 is a different class. So mu is equal to 0 is flat space, and mu different from 0 is plane wave. And any value of mu is equivalent to any other value of mu up to a boost, up to a rescaling of p minus. Yes. What? Yes. Yes. Oh, no, because here you get the absolute value of n. This is not the absolute value of n. Okay. So in normal language, the n positives are the left movers, and the n negatives are the right movers. Okay. So this in the massless limit is something like n left plus n right over p minus. Okay. And this one here is n left minus n right. So this is 0, and the other one. Okay. Yeah. Yes. Yeah, well, it's a solution not of Einstein's equations with a phi from fifth rank on the right hand side, right? This metric is a solution of the following action: r square root of gr plus f squared. Okay. What? Oh yeah, sorry. Yeah. Mm-hmm. Yeah. So the concept of massless particles makes sense when you have a Lorentz invariant space. so the concept of mass. This is not a Lorentz invariant space, so we can't define the concept of mass. Okay? So the question of whether it's massive or massless is not terribly well defined because we don't have a Lorentz invariant space. Right. So if we so what is true is that the spectrum is discrete. Okay. We don't have continuous spectrum. We have states with discrete energies in the light cone. If we have non-compact space, we normally have in the light cone spectrum with continuous energy that comes from the center of mass, degree of freedom in the transverse directions. Right? Here we have a discrete spectrum, and that's a reflection of the fact that particles are feeling this confining gravitational potential. In AdS, we also had I didn't emphasize that, we also have a discrete spectrum of particles. Okay? That's again due to this confining potential.
And you still can identify some
Yeah, we will be able to do that. That's right. So if you set n equal to 0 here, okay, so there are some states here in the string spectrum that correspond to n equal to 0. Okay, those are states whose energies are independent of alpha prime, right? So if we were to send alpha prime to 0, they would still have the same energies, right? So alpha prime to 0 will make massive all massive string states, and we'll be left with basically the mass, what were originally the massless states, so the fluctuations of the graviton and the phi form and all the other fields around the solution, and those are given by this spectrum with n equal to 0. Okay. Okay, so in this case, we have the particles are very massive. So here, this term is very small. We could even make a non-relativistic approximation, and in that limit, we have the string world sheet, and we have these very massive particles that are very localized and propagating along the world sheet. Okay. So that's the picture in this limit. Okay, so now what we are going to do is, let's see, let's erase this one. Now we're going to start with AdS 5 cross S5, and we're going to take a limit that will give us this plane wave that we wrote over here. And the reason we focus on this plane wave is precisely because it arises in this limit. So AdS, let's say, has spatial sections which are like hyperbolic space. So here I have tried to write a spatial section of AdS 5. And on each point we have this phi sphere, so this is the S5. Now we're going to do the following. We're going to consider a particular massless geodesic in AdS 5 cross S5. And this massless geodesic will be such that it's sitting at the center of AdS, okay? And it will be moving along a great circle of S5 as time goes on, okay? So if we write the metric of AdS 5 cross S5 as dr squared ds squared equal to r squared, so this is the first part is AdS 5, the second part is S5 written in some particular coordinates. Okay? So we are going to be interested in a geodesic that is sitting at rho equal to 0, at theta equal to 0. So that defines this point and this great circle. And moving, initially it's moving along this trajectory, so psi equal to t. Okay? So that's geodesic. And now we are interested in looking at the space-time that is very close to this geodesic. Okay? So the space-time very close to this geodesic will have the shape of this plane wave. Okay? Now this is a general feature. So if you have an arbitrary manifold and you take a massless geodesic and you look at the spacetime close to this geodesic, you'll get a plane wave. And this limit of getting close to a geodesic, of a massless geodesic, is called Penrose limit. Okay? So you basically look at the spacetime from the point of view of particles which are also moving at speed close to the speed of light along this geodesic. Okay? And so this limit can be systematically done by rescaling. So you define a variable x minus. Let's call this variable x minus tilde. And now we define a new variable x minus, which will be r square x minus tilde. And we are going to take a limit where r goes to infinity and x minus tilde goes to 0, so that we are going to be considering particles whose coordinate x minus tilde is very close to the one that defined the geodesic. So the geodesic was when, so the massless geodesic was when x minus tilde is equal to 0, and then we're going to consider particles where x minus tilde is very close to 0, but not equal to 0. Okay? So we are considering that region of the spacetime. And we are also going to rescale the rho. We're going to define r and theta equal to y over r. So y is not a good name here. C over r, okay? And now we take the limit, and then the other coordinate, the final coordinate will be x plus equal to t. So t we're going just to call x plus. And you can see that if you choose these coordinates and you make this rescaling, you go back to this metric, and you're going to find that the limit of, after you take this limit, you'll get the metric that is written above, okay? Where y squared will be rho squared plus, no, not rho squared, r squared plus c squared. So here we are taking also rho and theta to 0, keeping r, c, and x minus finite, okay? So we keep r, c, and x minus finite, and x minus and x plus finite. Okay? So for example, let's check some of the features of this metric. So for example, this term here, once we define rho this way, there is a power of 1 over r squared that cancels this power of r squared here. And inside this sign hyperbolic, we'll be able to expand this for small rho. So we'll get here d rho squared plus rho squared. The factors of r cancel. And so this piece in the metric will give us the dr squared plus r squared d omega 3 squared. And that's just the metric of R4. Okay? And well, similarly with the other factors. So this here we can expand this for small rho, and similarly this for small theta. And these two pieces, so the piece where we have 1 here and 1 here, will give us dx tilde plus dx tilde minus. One of them will absorb the factor of r squared that is multiplying the metric and give the dx plus dx minus. And then there will be another term that comes from the term that is here, quadratic in rho, quadratic in theta, and that will give us the second term in the metric. Okay, so that's this. So actually, if we do this limit exactly as I have stated here, we get that metric with mu square equal to 1. Okay, and you take the same limit of the 5-form field strength that you have in AdS 5 process 5, and you get that this constant 5-form field strength that we discussed here. Okay. Okay, and now, so on AdS, you have the energy of a particle is just given to t, and the angular momentum there is a U1 inside SO6 that measures the angular momentum that this particle has. It's given minus I d d psi, and then you can just translate. You can basically find that minus p plus of the plane wave. Okay. Let's see. So it's a simple change of coordinates to rewrite this as dx plus, and minus p minus is equal to minus p minus tilde. So p minus tilde is this derivative with respect to this variable over r squared. So this relation, this r squared, comes from the r squared here in the definition between these two. And this is equal to 1 over r squared. Of course, this is just the definition of the translation in x minus direction. Okay? And now dx plus and dx minus were expressed in terms of t and psi. So expressing them in terms of t and psi, and using these two relationships, we find that this is well, this is some let's say this is that, and this one here is 1 over r squared I minus d psi, and this is equal to the energy minus j, and this is equal to j over r squared. Okay. So we see that what will become p minus in the plane wave is related to j over r squared, and if we wanted x minus coordinate to be finite, so p minus we want it to keep finite, and r is going to infinity, so j will have to go to infinity. Okay. So in terms, first we express the limit in terms of coordinates, but of course we can express it in terms of the momenta of the particles that we are considering. And so j has to go to infinity, and r has to go to infinity, and j over r squared has to be kept finite. And similarly, this p plus is being kept finite, so the energy minus j it's also kept finite. Okay. Now, this is the energy of a particle in AdS in global coordinates. So now what I would like to do is I would like to re-express all these formulas in terms of the gauge theory variables. So we're now going to use the fact that AdS 5 cross S5 is conjectured to be equal to n equal to 4 Young-Mills, and we're just going to rewrite all these formulas in terms of these gauge theory variables. Okay, gauge theory notation at least. So the energy of a particle in AdS in global coordinates is equal to the energy for the CFT states of the CFT on a cylinder, okay, and the energy for states of the CFT on the cylinder, that is the same as the conformal dimension of operators of the CFT on the plane. Okay, that was one relation we saw, and this J will be the R charge, or the charge under one of the particular generators of SO6 of that particular operator. Okay. Now, here you remember we had this formula for P plus for the spectrum of the string, and now we can just re-express this formula in terms of these gauge theory variables, and so I'm going to do that here. So we find that minus P plus is delta minus J. So we find that delta minus J for that string state is again the sum over n to infinity. And now we have this P minus squared, and we express P minus in terms of J over R squared. So here we'll have mu, we said was equal to 1, so we have 1. Now we have this n squared that we have over there. The P minus becomes J, so we have a J squared here in the denominator. And we have an R squared here, and this is raised to the power square, so we have an R to the 4th inside this square root. And this R to the 4th is equal to Gn, G squared Young-Mills n. Okay? So that's the same formula expressed in terms of field theory variables. Maybe I can write it like this. And we are taking, so this limit is just saying that J over G square N is being kept finite. Well, okay. So we're taking a limit where the Toft coupling Gn is going to infinity and J is going to infinity, keeping that quantity finite. Are there any questions? Okay. So now, so all of this has been an analysis of what happens on the gravity side. So we took the AdS 5 process 5, we took this Penrose limit, we analyzed the spectrum of strings around this massless geodesic. So we are having here some little string that is moving very fast along the S5, and we calculated the spectrum, the string spectrum for those strings. And we re-expressed the answer in terms of these gauge theory variables. And now what we would like to know is whether we can reproduce this answer from a computation just real in the gauge theory. Okay? Okay, there are some states here that are easy to reproduce. So the states that are easy to reproduce are the states that came from massless particles in 10 dimensions. Okay? So those are the ones with n equal to 0 in this formula. Notice that states with n equal to 0 have energies which are independent of the Toft coupling. Okay? So if n is equal to 0 here, the Toft coupling disappears from the formula, and so we have energies just that are given by some integers. So these states look a little bit like BPS states, and in fact they will be BPS states. And we had said before that all massless 10-dimensional particles were in BPS states, and we're just observing the same property here. Okay, so let's find the simplest state. So the simplest one is the ground state of this massive theory. So this is the spectrum of a theory. So we have a theory on a circle, and it's a massive theory, so it has some minimum energy state, a unique minimum energy state. So in Lycon gauge, we have some state which we can call the vacuum with some value of P minus. And we would like to know what this state corresponds to in the gauge theory. Okay? Now, in perturbation theory, there is all states of the gauge theory obey that delta minus J is bigger or equal than 0. Okay? So in perturbation theory, delta minus J is bigger or equal than 0. Now let's see this more explicitly. So we have all these 6 scalar fields, and there is this SO6 symmetry. Well, let me draw the sphere here again. That the SO6 symmetry that corresponds to translations along this circle that corresponds to shifts in this psi coordinate, and that corresponds to, in this language, to a rotation in the, let's say, phi and 2 directions. So this generator J is the generator that rotates the first 2 directions and leaves all the other directions fixed. Okay? So it's convenient to define new fields, let's say C equal to phi 1 plus phi 2. So this field J has J equal to 1, and then we can define a field C bar phi 1 minus phi 2. This field has J equal to minus 1. Okay? And similarly, we can define some other fields, let's say W1 and W2, which are complex combinations of the other two, and then these and their complex conjugates will have J equal to 0. Okay? So this scalar field will have delta minus J equal to 0, and this one will have delta minus J equal to 2, and all these ones will have delta minus J equal to 1. Okay? This is a computation in perturbation theory, and we can do a similar analysis for the fermions. So the fermions have a spinor index under this J, so there will be fermions that have, some of the fermions will have J equal to ½ and some of the fermions will have J equal to minus ½, and all these fermions have conformal weight delta equal to 3/2. So some of the fermions have delta minus J equal to 1, and some of the fermions have delta minus J equal to 2. Okay? Okay, so let's see, what should I erase? I guess we can erase that one there. Of course, the gauge bosons or the field strength does not have any J, so it has delta minus J at least 2. So we should count here the dimension of some operator like F mu nu that has delta minus J equal to 2. Has J equal to 0 and delta equal to 2. Okay, so now we see that if we want to construct an operator which has delta minus J equal to 0, like this one, so this operator has P plus equal to 0 is the ground state. So here construct some operator that has delta minus J equal to 0, and the only way we can construct it is with this C's. So this operator will be trace of C to some power, and the power is just given by the U1 charge, so the power is just J. So that's the operator that corresponds to the ground state. Okay? Are there any questions? Okay, so now, now let's get the string spectrum. So let's get the perturbative string spectrum. Sorry. Let's get the first the spectrum of particles that are massless in 10 dimensions. So we're going to now match the spectrum of massless particles in 10 dimensions. So they're massless in 10 dimensions, and they correspond to, in this formula, to particles with n equal to 0. Okay? So we see that when n is equal to 0, delta minus J is basically equal to the number of particles we have, number of oscillators excited. Okay? Where each bosonic and fermionic oscillator contributes basically with 1 to delta minus J. Okay? Is this clear? Yes. Okay, so now we come back here and we see, well, what kind of fields can we add that have delta minus J equal to 1? Well, we have this fermionic, well, let's start with the bosonic fields. So we have all these 4 bosonic fields, okay? We can also add operators which contain derivatives, for example, the I of C. So these are also have delta minus J equal to 1. So let's consider here the fields with delta minus J equal to 1. These are the elementary fields, and then from them we were going to construct the operators. So we have, let's say, I need a better notation. So we have these WIs, so I from 1 to 4. Well, there I call them, okay, I from 1 to 2. So here we have 4 fields, 4 real fields, and then we have 4 derivatives of C. So again, we have 4 fields. And then we have the fermions that have R charge a half, and we basically started with 16 fermions, and the ones that have R charge a half, this will be 8 modes. Okay. So we have these 8 bosonic fields and these 8 fermionic fields. Okay. So now on the theory side, let's consider first of all the simplest, one of the simplest states we can construct out of the Lycon vacuum, and that's the state that results from adding, let's say, one massive boson that corresponds to an oscillator, let's say, in a transverse direction. So we add one bosonic 0 mode, A0 dagger, 0. This 0 means that we have n equal to 0. We add this to we add this, and this has some index I, which labels which of the 4 oscillators in the transverse directions we have. Well, we have 8 oscillators, and we're going to choose them in the second 4 transverse directions. So this seems to correspond to, we'll have some state C to the J, Wi. Okay. So this will correspond to this operator. So we add one of these W's. And this we can understand fairly simply, that this should be the case because the states 0p and this state are related by a symmetry. So if you start with the operator with the string state with 0p and you act with some of the generators of SO6 that do not commute with J, you will create this mode on the worldsheet, and you will transform this operator into this other operator. So this other operator is an operator which is again in the same SO6 spherical harmonic representation as the operator C trace C to the J. So they are just related by the action of the symmetries. All right, so that was simple. Now let's consider what happens if we act with 2 of them. So let's say A1, 0 dagger, A0, 2 dagger, on 0 B minus. Okay, so how do we? So we can now apply the same argument. So this operator is again related by the action of a space-time symmetry. That is a space-time symmetry that is broken when we choose this direction P minus, when we chose this geodesic, that breaks the symmetry. But the full theory still is in representations. I mean, all the states fit into representations of this full symmetry. So when we act on this state, we'll get some other state in the same representation. So its properties are determined by representation theory. In particular, the conformal weight will be related by that. And so here, when we act twice with the symmetry, so when we acted once, one of the C's, so we started with C to the J plus 1, and one of the C's got changed into a W, and now 2 of the C's will be changed into a W. There's one point I didn't explain, which is one of the C's was changed into a W, but no matter which of the C's was changed into a W, we can always reorder this expression and using the cyclicity of the trace and put the W, let's say, on the right-hand side. Okay? Here, order will be important, and order will become more important when we okay? So now order is important. One of the W's can be put in the beginning, but the second W we have to keep track of its position along this string, along this set of C's that we have. And so this is the expression that would correspond to this operator. Okay? And this we just got by acting with these symmetry generators. Okay, are there any questions? Yeah. Yes. Well, little n equal to 0 means that they correspond to particles here on the string that has 0 momentum. So you make some excitation, and this particle is not moving along the string. So it's in a 0 momentum wave function. It has a wave function that is constant along the string. Okay. Yeah, this is the number of oscillators with n equal to 0. Okay. Each mode is a harmonic oscillator. Even the mode with n equal to 0 is a harmonic oscillator. This is different than the standard string, where the modes with n equal to 0 are just momentum modes. Here, the modes with n equal to 0 are harmonic oscillators. So I was referring to these harmonic oscillators. Okay. Is that clear now? With the usual string, well, the reason this happens is that you have a gravitational potential. Your spacetime is not flat, and there is a gravitational potential that looks like a harmonic oscillator. So when particles move there, they feel as if they are in a harmonic oscillator. Potential, I mean. I don't know, particles that fall through the center of the Earth feel as they are in a harmonic oscillator potential. Okay? So it's not very different. So the constant phi for field strength is like the constant, let's say, this is very qualitative. It's similar to the constant matter density of the Earth that gives you the harmonic oscillator potential. This is roughly speaking. I mean, it's not exactly the same because the light symmetries are different, but conceptually it's rather similar. Okay. Okay, so those are these modes, and all these modes, of course, this will have delta minus J equal to 1. This, of course, will have delta minus J equal to 2, and so on. And these are protected by the symmetry, so this we can compute a weak coupling and it gives us this, but even at strong coupling we'll have the same result. Okay, so this is very nice, but this is just what's predicted by the symmetries. So here we are not learning something terribly new. So we learn something from the matching of the first operator, and the matching of all the other operators is just a consequence of the symmetry. However, something we are learning is we are having an idea of what the expression is here for the operator. Now, if you remember the discussion about the Toft diagrams, so we expect that the string comes out of the interactions among gluons, and here we are starting with a state that has all these Cs, right? So it has all these double lines, and these are all the double lines corresponding to the Cs, right? And so they are propagating, and we have some other objects like this W here in the middle, okay? We have one here, and then we have another, a different kind of W, let's say here, and we have all these double lines, okay? And this is this is sort of the free contribution, but of course there are all kinds of interactions among these lines, and for BPS states they all cancel out, but these interactions are precisely the things that will build up the string of that Toft was talking about, okay? And that string is precisely the same as this string we are talking about here, okay? So we really should think of this set of operators as giving rise to some kind of, in this case it looks a little bit like a lattice of sites. All these Cs define these lines, and then these other operators, we can call them impurities because they are different from the Cs, but there are very few of them in the large shade limit. And these ones will be sitting here somewhere in the middle. So we have here one of these W impurities, and here one of the other ones. And we should think of that as roughly this string here. So this picture gives us an idea of how we should look for states with n different from 0. Okay? So I guess I don't want to erase this formula. So states with n different from 0 will involve there is one point I forgot to mention, which is that when we think about this lattice here, you see here we are summing over all positions where these impurities can be put. So this is roughly the same as saying that these impurities have a constant wave function along this lattice. Okay? And that's related to the fact that n equal to 0 modes have constant wave functions along the string. So if we have something different, n different from 0, we expect to have here a wave function with momentum along the string. Well, that's what we have here. It's not that, and that will translate into something with momentum along this lattice. And so this will be something like you have this. You will insert this impurity, let's say W1 or W2, at any point in the string. And before, so when we were n equal to 0, we were just summing over L. But now, besides summing over L, the sum over L will include a phase factor, which is e to the 2 pi I L over J. Okay? So we'll times n. So this is like momentum along this lattice. That's the same as the momentum that wave functions have here. And so so this is the natural conjecture for what the states with any different from 0 should be. Okay. Now, it turns out that if you consider an operator like this, like trace of this quantity, this operator is actually 0 because this particular operator is 0 because the W here can be put in the beginning by a cyclic transformation, and then the sum of all these phases gives 0 if n is different from 0. Okay. So we might be worried by that, but then we should remember that this would correspond to something where we have one oscillator, a single oscillator acting on the Lycon vacuum. But this is not a state in the spectrum because n is different from 0. Oh, I erased. So here, remember that there was this constraint that the momentum, which is sum over n, and n, should be equal to 0, right? So, so this state is not in the string spectrum. So more generally, we see that the fact that the trace is cyclic, so the C of the trace corresponds to this translation invariance on the string watershed. So it's related to this constraint that P is equal to 0. So this is related to the translation invariance, right? Is related to the fact that translation invariance is equal to a gauge symmetry on the watershed. Okay? So any state that is not translation invariant, here is projected out, and here is automatically 0. So the fact that the trace is cyclic will set it to 0 automatically. So if we want something that is non-zero, we need to consider on the string theory side at least two different oscillators, one with momentum n and one with momentum minus n. Okay? In other words, in the usual notation is we want one left mover and one right mover. Okay? Notice here we're denoting the, let's say, left movers with minus n. Normally minus n is the destruction operator and so on. Here, these are two creation operators, one with positive momentum, one with negative momentum. So now this is in the spectrum. And so this will correspond to trace of, let's say, W1, and this sum between 0 and j. So this is the operator that corresponds to this state. Okay? So now one exercise that we can do is, so this operator at weak coupling has dimension, has delta minus j equal to 2 because it has two of those impurities, two of these W's. And we can ask whether we expect corrections or not, right? So if we look at this formula, we see that there is some chi-square-n dependence, and in fact, we can expand this formula when this ratio of chi-square-n over j is small, and so we get in the result in string theory. So let's say the string theory result is this is 2 times 1 plus 1/2. Well, some number here. I didn't write down the precise number here, but you can easily compute that number. Well, I can just write it down to get the complete expression. Well, you can find it in the notes. You can find the precise number in the notes, and you get this to first order. Okay? Okay, so plus, well, of course, further corrections which are higher order powers of chi square n. So this result in string theory looks this expansion looks like the expansion we would get at weak coupling. So you can ask, well, what happens if we compute in gauge theory at weak coupling? So at weak coupling, you start with that operator, and you have to consider the Feynman diagrams that correct its conformal weights. Okay. Okay. So in order to consider that, we take this operator. The operator, let me call it O. So O is this operator. And we're going to consider its two-point function. Let's say O0, O at x. X, these are points on R4. So this is in the CFT. We consider this two-point function. Okay. So the leading behavior of this two-point function will be 1 over x to the twice its conformal dimension. That's what we compute at leading order. I mean, this delta 0. So delta 0 is equal to j plus 2. So this is what we get to leading order. And then, if we compute the first correction, what we are going to find is that here we'll have a correction which will look like chi square n times log of x. Okay. Now, the reason you get the log is that what you are really doing is you are expanding. So this is really what you get if you actually do the computation, log of x over some cutoff and so on. So what this log comes from the fact that we are expanding this formula, which is 2 j plus 2 plus some number times chi square n. And if you expand this formula to first order in chi square n, the first term is just chi square n, chi square log x. So we are really looking for something that for the coefficient of this log. Okay. Okay. Now, so we have this operator O here at the origin, and we have O dagger. Well, I guess what we have at X is the complex conjugate of that operator. We have all this bunch of C's. In order to get the non-trivial construction, we need the complex conjugate, and we have O. So this operator O is trace this W, C to the L, W, C to the J minus L. And this is a similar thing with all these things replaced by their complex conjugates. Okay, so let's first think about the operator with no W's. So here this is given by a contraction of all these double lines, of all the C double lines. Okay? And this has to be done in the proper order. So once we contract one of the C's with one of the C's here, then the C that is to the right needs to be contracted with the C that is to the right, and so on. Okay? So the order is important. Okay, so the free diagram then will consist of this times we'll have a W and a W1 and W2. So W1 will be, let's say, some line here, and W2 some line over here. Okay? And then we'll have to sum over all these lines, and this, of course, will give us a simple power of 1 over x2 minus x2, because these are just the free propagators. So the corrections will start appearing when, for example, some of these lines exchange a gluon. So here we can exchange any particle, or we can have, let's see, So here we can exchange particles, we can have loop corrections to these lines, and so on. Okay, and all these things will contribute. Now, any one loop diagram or any interaction that does not change the position of these lines will basically be something that we'll have to cancel out, because we know that the one loop corrections cancel out for the states that were BPS, so the states when L was equal to 0. So if L is equal to if n is equal to 0, if the momentum along the string is 0, then we know that all those corrections should cancel out. So the only corrections that could possibly not cancel out are corrections that depend on the phase. Okay, they depend on they will change the positions of this line in such a way that we'll get one phase factor here and a different phase factor on the top. Okay. So let me be a little more concrete on an example of such a correction. So suppose you have all this diagram, and let's say this blue line is sitting here at the origin, defines some kind of origin for us, and now the green line is going to be doing the following thing. So we come here with a green line here, there is some interaction here, and then this green line switches position with the C line. Okay. Now, so here, this operator here will come with a phase factor that basically counts how many C's there are to the right, to the left of this insertion. Okay. So we have a sum of terms, and the only term that will look like this is the one where, let's say, that L that appears there, in this case, would be equal to 4. Okay. For this operator. And this operator here, we have a similar sum over, let's say, L prime, and here L prime is equal to 3. Okay. So here we'll have one phase, and here we'll have a different phase. So this will contribute with some net phase, which will be e to the 2 pi I n over j. Okay. Now we know that if so we have this diagram on one hand, and now this diagram comes from this diagram could appear from the Yang-Mills interactions. So the Yang-Mills interactions include let's see, where should I write that? So it includes this term in terms of the scalar fields that well, it has this sum over I and j, and well, these terms will contain terms that are of the form, for example, C, W, C bar, W bar, and so these kinds of terms are the ones that will give rise to those interactions that exchange position. Okay, so here these two terms, let's say these two terms annihilate the C lines here, and they could be with one sign, and then here we could have either of the two with two different signs. So basically this interaction vertex is giving us this contraction with one sign, and then the other contraction has the opposite sign. So let's say this comes with plus sign, and then the other one so from the two orders that you can choose the same order here and here, or the opposite order here and here. And so one, let's say this one has with plus and this with minus. Okay. So this will come with no phase factor. This will come with phase factor equal to 1 because we didn't change the net position. And this will come with phase factor e to the I 2 pi n over j. Okay. And this comes with a different sign, and this sums. Okay. And similarly, we can consider the diagrams that change it in the other direction. So there could be diagrams that, by considering the same vertex, you can have something that does this, okay? And this will come with the opposite sign in the face. If we had here e to the 2 pi I n over j, here we can have e to the minus 2 pi I n over j. Okay? So the net result of all this discussion is that this type of diagram, so here we have two propagators that come up to here, that's some power of x, and then we have to integrate over this point. The integral over this point will diverge like a log, that will give us the log, and in the end we get a term that goes like g square n, okay, times cosine of 2 pi n over j minus 1, okay, with some coefficient here that we can compute times the log. So this is the coefficient of the log. And now what we say is, well, we want to take the limit when j is very large, so we expand this cosine around large j, and so we get g square n times, so the first term here in the expansion is quadratic in n, so we get n squared over j squared with some other coefficient here. Okay? And the interesting feature is that the number that appears here is actually equal to the number that appears here in the string computation. Okay? So that was the gauge theory computation, and this is the string theory computation. Okay, so in this way, from this type of gauge theory computation, we have reproduced the spectrum of strings in this limit. Okay. So we indeed are seeing strings and from a gauge theory, and these strings are moving in 10 dimensions. Okay. So here is an explicit sort of demonstration that the strings that come from the top limit of n equal to 4 Young Mills are strings that move in 10 dimensions. So we calculate the spectrum of the operators and we match it to a string that moves in 10 dimensions. Now to do this more precisely, we would like to compute corrections here. Well, let me first say one word that you can ask whether this computation really had to agree or not. Okay? So did this have to agree, or maybe we could have found something different here. Okay? And so I should point out that these two computations are really done at different regimes in the 't Hooft coupling. So this computation here was done when g square n was much bigger than 1, and this computation here was done for g square n much smaller than 1. Okay? So in principle, if they had disagreed, you could argue, oh, maybe there is here some function of g square n, and this function has one limit when g square n is small and another limit when g square n is large. So some constant on one value and some constant on a different value. For large g square n, a different constant for small g square n. And this we already saw that this happened, for example, for the free energy. Okay? But here it does not happen. So this is a hint that there should be there should be some argument that that this function is actually 1. Okay? That this is a computation that is very close to a BPS computation and will be protected. So there was basically one argument basically like that, which started with the n equal to 4 Young Mills and looked at some identities that correlation functions should obey on the basis of conformal symmetry, and looked at this, how these identities looked at a very large J, and they not only found here actually that computation, what that computation found was that the answer had to have a certain J dependence, and the J dependence that it had to have is that this had to be, so this is the string theory result, so the gauge theory result had to be such that delta minus J for each of these impurities that you're adding should have the full formula with the square root. Okay? So this full formula, with some coefficient here, and they really did not determine the number. Okay? So you can explain why you have the full square root, and then if you expand for small value of J, you compare the coefficient in this way. But I think there hasn't been a really clear and transparent argument for why this coefficient really has to agree between gravity and the gauge theory. Okay? But there's been an argument explaining why when you compute, when you iterate these corrections, you will get this formula with the full square root. So getting the full square root is really amounts to getting really the full string spectrum in this full plane wave. And once you get the square root, you can consider here other ratios, like ratios where this factor is much bigger than this, which is basically the regime in which we are in flat space. Okay? So this is really a derivation of strings in almost 10-dimensional flat space from the gauge theory. Okay? Now there are many other things you can do with this. So one thing that was explored a lot was string interactions. So here we discussed only these planar diagrams where we have just a single trace operator, but you can have you can consider situations where you start with one single trace operator and another single trace operator, and you have a non-planar diagram that connects these two in the gauge theory, and then you can compare what you get by computing these non-planar diagrams with what you get in interacting string theory. Okay, with the interactions you get in string theory, and after long discussion now, agreement has been found between these two computations. And another interesting development, especially in this last year, was the analysis of these conformal dimensions. So exactly this calculation we did here, but not for large J, but for finite J. So you can do this computation for finite J, and you can find this the analogous thing to this result. So not a cosine, but some function, some number that depends on the string state that you are considering. So not on the string state, sorry, on the operator you are considering. So you write down an operator with a finite number of fields, and you consider you compute the one loop corrections. This will give you something, and it turns out that this computation of computing this operator turns out to be equivalent to considering some kind of spin chain. So you can think of these operators as a lattice with a spin on each side, and this spin on each side tells you which kind of operator you have on this side, where you have a C, a derivative of C, or you have a W, or you have a gauge boson, etc. So that's like some variable at each side, and then the interactions among sides, you can think of that as interactions in a spin chain. So the one loop result will give an interaction between nearest neighbors, and it turns out that this interaction is such that the full Hamiltonian of this theory is integrable, and this is sort of an interesting result. So there is this one loop integrability people see at one loop. And also, if you consider so here the results of finite J and finite Chi square n are results that should be compared with the string theory in AdS, where the radius of AdS is small. Okay, it's very small because Gn is very small, and well, we don't know how to do those computations, but you can write down the sigma model, and well, first Polshinsky, Royban, and other collaborators show that some aspects of this sigma model were integrable, and I guess Nathan and collaborators show that even when you include ghosts, that's integrable, right? Yeah. You showed it. Did you show it? No. You showed it. Yeah, sorry.